Okay, shall we start? Come on. Hi, I'm Mark Wielaert. I currently work for Red Hat, and they actually pay me to hack on SystemTap, which is fun. Some of you may know me from some of my Java work, and if you were thinking, oh, Mark is going to talk about Java, that's going to be a bit disappointing. There will be one example at the end using SystemTap with Java, but all the rest is boring, old school languages. The talk itself is in two parts. One about SystemTap itself, why do we need it, what can it do, some examples. And the second part is, well, also about SystemTap, but what we need besides SystemTap to make it really useful. And what you could do with your programs to make SystemTap and observability on GNU Linux better. And then there will also be a little demonstration of, indeed, with Java, how you make something like a Java runtime more observable with SystemTap. Well, it's not really a circle, but kind of a circle. So why do we want to have something like SystemTap? If you are looking at what your system is doing, there are a lot of nice tools. You can do profiling with top to see what's running on your system using OProfile or the new perf tool. You can use some tracing tools, strace to trace your system calls, ltrace for library tracing, the new ftrace tool to trace kernel function calls. And of course, if you then have figured out what is going on, you can drop into the debugger and really inspect what is going on. Kind of the problem is that these are all separate tools. Profiling tools often work system-wide, while tracing tools work one application at a time. And with debugging, you often just stop your program to inspect what's going on. And with SystemTap, we wanted all the advantages of these programs without any of the disadvantages. Of course, that also means with SystemTap you give up some things you can do with the other tools, but we hope that with SystemTap you have at least one tool that keeps you going for a while without having to switch between these things. So, the tracing tools. What's nice about tracing tools is you can see what's happening while things are running. It's often faster and nicer than printf debugging because it's fully automatic. Printf debugging. You get a quick overview of your code flow, but the limitations are there of the specialized tools. You either can trace system calls, or you can trace function calls, or you can trace the kernel. And there's often limited filtering, which means that you quickly get too much information And when you try to grab it out and your system is really busy, you might actually end up changing the system you're observing. With profiling, the nice thing is that it also runs while your system is running. And it gives it samples, and that means you get statistics about what is going on. And you often can see system-wide what is going on, whether it's in a library, in your kernel, in your program. But it is often limited to time sampling, and it would be nice if we could sample every interesting event. And often it's a large data dump. You profile for a while, and then you have all this data which you then analyze after the fact. Although there are really nice after the fact analyzers for the various profiling tools. And with debugging, we have the full context of what we're observing. Often you can access the variables, the parameters of the functions. You can look in memory registers, you can get a backtrace. You even have conditional breakpoints, so you could actually run a program and only stop it if some context is interesting. The limitation is, again, it stops the program under inspection, which is nice if you want to sit down and look what's really going on, but it's not so nice if a problem only occurs on your production system and people are actually using that system, and you would rather just look at what is going on and not stop a server. And with debugging, again, it's one program at a time, not system-wide. So, with SystemTap, we kind of made a mix. It is unobtrusive, difficult word, non-stop, so you can look at your system, but you don't halt your system or allow it to hold up your system too long. It should be system-wide. You can monitor multiple events, both synchronous. This happens now, a function call, enter function call is exited, and asynchronous based on time. And it is scriptable, so you can do in-place filtering, so you don't have to filter after the fact, and you can collect statistics in place. It's not super powerful, but powerful enough. What we wanted was to make all this safe. So enforce that it is non-stop, unobtrusive, doesn't use too much memory. SystemTap will allow you to monitor things, and then if it notices your monitoring takes too long, it let the system run. You can override that, but by default, you're not allowed to do anything dangerous, use too much memory, use too much time, that kind of stuff. So, how does it look? It's a pretty simple setup. Basically, you have a probe, you probe an event, and you have a handler for that event. And that event can be something like a function entry, for example, in the kernel, or it could be a specific statement in a process that gets passed, or it could be a timer that triggers the begin and end of a script is an event. We did that so in the begin event you can set something up, and in the end event you can create a report from all the statistics you collected. There's this idea of aliases, so you can alias multiple interesting events as if it is one. There will be an example of that. And a handler can do simple filtering on some conditionals in the context of the probe, and then it can immediately say, oh, don't do that, I'm done. And there are simple control structures. For each is for the, you have associate arrays and statistical variables, and you can loop over those. Of course, there are limits that see, oh, it did too many steps. It is limiting the whole system too much. And that is kind of the default. We always want that there's no noticeable impact on the system unless you explicitly specify, yes, I want to use megabytes of memory and I know what I'm doing. Yeah, sure. And there are three kinds of variables. So you have primitives, numbers, strings. You have associative arrays and statistical aggregates, wherein where you can store values, and you can get the count, the sum, the average, the maximum, the minimum out of it. And of course there are some helper functions for actually logging something, printing, getting the time, what is the current process, that kind of stuff. Well, I show some examples. This is the simplest. You invoke SystemTap as step. Either you give a script on the command line, or you have a script in a file, and you can specify a target process if you want, which actually means while this process is running, this script should run. And to see what kinds of events there are, you have the step -L list, and you can give it a pattern of events you want to see. And if you use -L, you actually get all the context variables also. So I'll show some examples. I wanted to do it without any tricks and just have Fedora 12 installed. And Fedora 12 is really nice because for a couple of contexts, it really helps to have debug info available. And the latest Fedora has a backport of the variable tracking assignment patches for the next GCC, so the debug info is really nice. It has SystemTap nicely integrated, it has the latest kernel. I had to do some tricks. So I did install all debug info beforehand, because otherwise it would be a bit long. SystemTap will tell you if it needs specific debug info files. So I did that. I added myself to the SystemTap group, so I can actually, that means I've elevated privileges so I can actually see everything. There are a couple of different groups you can put users in, so they can only use some scripts, and there is a unprivileged mode in which you can only inspect your own programs. And I actually installed the Python and Java packages from the rawhide version, because the version in Fedora 12 didn't have all the probes that I wanted to show. I believe the Java package is actually going to be updated, and next week it will be in Fedora 12. So, let's see. Oh, help. Yeah. So, to show that you can do some simple tracing, you can probe a process, bin ls, show me all functions, and just log the probe point where you placed the probe. And then we actually run it over bin ls. Oh man. Functions, okay. Function. Right. Yeah, sorry, the resolution is a bit. But what you can see is that it actually put probes on all the functions. This is actually a function from an included file. And nice thing is, this is also how you can actually specify the probe points. So you can also specify them as they would be found in the source files. And it can do that because the debug info files have all the knowledge of how the source, the binary maps back to the source files. And to show you can also have some, let's only print the probe function and show its parameters that what did I do? I actually wrote this out. How do you? Okay, sorry. Right. So here you see that again in a hugely big thing. Sometimes it cannot find all the context. So for example, here the print color indicator doesn't actually know what the parameters are, but for most functions it can actually see what arguments were given. To actually show a bit that you can also format it nicely, because this is just too much output. Here we actually use we probe each function call, and then we print out, we indent, we add a bit of indent to the current thread, and on each return we decrease the indent and we show arrows if we're going into a function or come back. If we probe and trace in this way, you can actually see, now I can show you that it's also system-wide, because I forgot to actually give it a target process, but I can actually run ls here. And it saw the ls running on my system. The thread indent function also prints the number of milliseconds, the process name, and the thread ID. And here you can see that, well, you can use SystemTap as a fancy L-trace, but you can actually nicely format and filter all the results. And no, let's skip that one for a minute because we're running out. This is all process-based, but you can also trace on probe. Cisco open. Show all the files that are being opened on the system at this time. So here we're doing system-wide probing. We probe, whoa, okay. You can see that GNOME settings is opening proc mounts a lot. And SendMail opens proc load efforts every second. Interesting. What did I want to say? Oh, I just wanted to show that you can do system-wide tracing and get output. The problem here, of course, is you get quickly too much output. Who is really doing something? Screen is a bit small, but the idea of this script is that you have some globals, which are actually associate arrays, and for every virtual file system read and virtual file system write, you for each executable you add the count of what they were reading and writing. And then you see a timer-based probe, which we actually don't use as a probe, but now as outputting all the data we collected. So we go through the names in the writes and through the names in the reads. We create totals, and then we print everything, and then we clean up. And oh yeah, 5 seconds. So yeah, luckily the thing happened. What I wanted to show is that even now, but this is a very quiet system, you already see that by outputting all this, you can already have step IO be on top of what you're tracing. To help a bit with that kind of anomalies, you can also use statistical variables where you every time put in the next number in. What it will actually do, if since we don't actually print out this global step, will actually run this program, and when we quit it, I hope, yes, it actually prints out for everything. It monitors the clock applet, it did 2 reads, the minimum read of 1,000 bytes, the maximum is the same, the sum, of course, then 2,000. On average, it did a read of 1,000 bytes. Okay. So, what I showed is with SystemTap you can do fancy scripting of all these events, at least. But we need something to observe, and for that we need events that we want to observe, and we need to have some context. Most of what I showed was very low level, and I think we nicely covered the low level stuff. You can have timers, you can monitor processes, signals, function calls, you can monitor in the kernel, and we're working on data watches that you can actually watch data being changed, and we hope to have events for the performance counters in newer CPUs. And especially for C, C++ based programs, the debug info is pretty good these days. So GC provides us a lot of context. The trick is a bit to get all these techniques also used by other tools. We actually hope that all the tracing, profiling, debugging tools also use some of what we're using, because then you get more people hacking on more of these low-level events. But what we really would like is more high-level events. So we have two systems for that. So you can write tap sets. That's basically the aliases. So we have a tap set for the virtual file system, and it defines probes, and it aliases those to the correct kernel functions, and it knows which arguments contain what, and then sets up the context for you. And that's really nice, but what we would really like is that kind of context, not that we code through the kernel or a program or something you want to observe and then somebody goes through all the source code, but we would like them in the source code. Where the developers write their code and they say, this might be an interesting point to observe. This is an event, and here's some context for an event that might be interesting if you want to know what my program is doing. And this is where you can help. I mean, you write programs, so. In the kernel, we're making nice progress. There are actually 2 solutions. Well, to be honest, the kernel markers are being deprecated, and the trace points are the new way to do it. SystemTap can observe them both. And of course, there are a lot of tap sets already for the kernel. For user space, we are trying to do a trick. there's dtrace, which is kind of similar in spirit to SystemTap. Unfortunately, it's not really suitable for GNU Linux systems, and well, that's basically just because the license is completely incompatible, and oh well. But they had a great idea. They have user-static dynamic probes, which is macros which you put in your program to indicate here is something interesting. Actually, we had the same idea and we did it slightly different, and then we thought, well, that this is actually not nice, because then we make people choose, do you support dtrace or do you support SystemTap? So we're actually discouraging people from using the step probe indicators and encourage people to put dtrace probe macros in their source code. And the implementation is completely different, but if you compile your program on a Solaris system, it will make those events visible to dtrace, and if you compile on a GNU Linux system, SystemTap will see them. And we even provide a fake dtrace script that kind of does the same things in your build. So there are actually a couple of programs like Postgres which already have those, and if you configure with enable dtrace, those probe points get put in and you can see them through SystemTap. Where should you put your probe points? What are interesting events? And most of the times that is when you would add a verbose flag and say, this is happening now. In those cases, it's often nice to also have a static probe point there, because with a verbose flag, or if you use logging, you are controlling what the user sees, and often they know better. They know they want to see something in one run or on the whole system, and they only need some context. One interesting thing was when we implemented SystemTap itself. So of course we have -v, and it parses the script and it compiles the scripts, and so it has a couple of passes. And I was actually adding the verbose output. Oh, I actually want to know how much memory this is using. Oh, I print out the memory and the timings. And then suddenly it was, oh wait, but I have a better tool for this. Because if you have these probe points, then we actually provide functions like the memory the process is using at that time, or the time a task spent. And we actually provide the actual values, not just the strings, so people don't have to parse out your -verbose output. And what was funny was that we added probes to each pass, so you can see, stop, start phase 1, the compile phase, and you can see it end that phase, and you can see it start and stop the parsing phase. And what is interesting is that now we can actually run this verbose output system-wide. We just run our test suite, and because we have aggregates, we have statistics, you can actually run the test suite, have a little script, monitor all the stop passes, and then say, on average, pass 3 takes the most memory, and the argument at that time was this particular script. Am I going too fast? Well, no. I'm on time. Okay. I'm going a little too fast. But that just means you get to ask more questions. Another way to use this is to make things that aren't C or C++ or the kernel or like scripting languages or a language runtime more visible. Actually, now I have time for a little story. It was kind of interesting because we really wanted these dtrace probes to be completely compatible, so people could just put those probes in their programs, and dtrace would see it, and SystemTap would see it, and the whole world would be happy. What was funny was that then we tried to see how Python was instrumented. And one of the sad things is that dtrace is actually forked in a Apple macOS version of dtrace and a Sun, now Oracle, I guess, or a Solaris dtrace. And neither of them actually submitted their probe points upstream. So we actually tried very hard to be compatible, and now we might actually submit our version upstream, and then they still look slightly different. It's not a big difference, but the argument order and the precise probe point names are different on macOS and on Solaris, which is kind of silly. Anyway. The nice thing in the Python case was that it was already kind of done. We just had to pick either the Solaris or the Apple version. And indeed, when you compile Python this way, you get a couple of probes, but the function entry and the function return are the most interesting ones. And again, we do some thread indenting to show the flow, and the argument names are not that nice, but I believe argument 2 is the function name, argument 1 is the file name, and argument 3 is the source line. Yeah, that must be it. Well, we can just run it. Ah, forgot again, but that doesn't really matter. Yep. I didn't even do anything in Python yet. But as you can see, now you can actually see inside your Python program. You can actually see what functions are entered when, where they were defined in the source code. One thing we don't have for Python, but we do have for Java, is backtraces. That's sometimes a bit more work. This means that you can now kind of instrument and look into your Python program as if it was a normal C program. Well, at least according to SystemTap. I probably should show that we can do the same with Java programs now. Java was also nice because, at least in the case of Hotspot, which was the Sun VM, which is now under the GPL, they actually spent a lot of time to instrument all the interesting parts. So you can now see when your Java program starts a garbage collect, or when it loads a class, or when it unloads a class loader. And the nice thing in that case is that you can also combine it with your other probe. So you can see, hey, when was some swapping out of memory going on in the kernel? Does that correspond to my garbage collections? And the nice thing is that, maybe I just do one example. Yeah. So in this case, for example, what's nice is that since SystemTap can look through the whole stack, you can get an interesting backtrace where you actually see. So what I actually did was when the GNI Java native interface get argument length is called, give me a full backtrace of this point. And what you can see is that it can not only show Java functions, method calls, but it also knows whether it's jittered. Well, this was just an hello world program, so probably nothing is compiled, but it knows whether it is interpreted. It can see some parts of the everything is interpreted. That's not fun. Otherwise, it could see some of the compiler work, the actual hotspot methods, like at the start, where you can see the setup till you actually hit your Java main program. Okay. Shall we take some questions? Wait, I must at least give you these two URLs. All my examples were a bit simple because I didn't have that much time to explain everything, but there's a really nice examples page, and there's a beginner's guide which explains a lot about the examples. And there's also a wiki where you can learn how to precisely put user space probes in your application. Yes. Can we use this, or?
Yeah, can you tell us a bit more about the performance impact of doing a system tap on kernel calls, syscalls?
So we try to keep the overhead really low. I'm not sure what our thresholds precisely are, but every probe is executed in place, so there are no context switches, and in principle, all the logging is just dumped in a buffer, which is read later. So the impact is pretty small for most things.
Hello. Is there the ability to define a priority in terms of repartition of resources between the monitoring activity and the production activity?
Sorry.
Is there the ability, if you take the example of SNMP protocol on routers and things like this is always defined as the lowest priority. And is there the ability to define a priority in terms of the right execution of the things on a system and the monitoring activity?
I haven't really thought about it. SNMP is that was what you were asking. SNMP, it's well, it's a higher level thing. This is much more lower level.
Any thoughts on using SystemTap to determine memory usage of kernel modules? So go, what's this kernel module using? Why is it chewing up that much memory?
You can partly do that. There are actually trace points on kmalloc, for example. So you could trace that and look at the color of kmalloc and map it to a module. I'm not sure, there might be something like that in the examples. Probably not precisely for modules, but there is something for how much kmalloc is called from where.
How much of the debug info is SystemTap understanding? For example, how can it print a struct?
Yes, you can. SystemTap sees the debug info for the struct, and you can actually dereference and get the fields of a struct.
Maybe it's a little bit of a silly question, but would it be possible to implement this for Windows?
I don't know.
Because Windows has, of course, a lot of tracing possibilities, and it's always nice to have similar interfaces.
Yeah, let's say it has been 10 years since I used Windows, so I don't know. Sorry.
Thank you.
Is there a library with a programmatic interface to it? So, for example, could Python look at the profiling information of its own probes and expose that within Python?
No.
Is that being considered, or is that interesting?
Well, maybe something like that could be done. I believe Ruby has something like that.
But has there been any discussion of adding anything like that?
No, not yet. To be honest, that was one trick. The Python support was
Not necessarily
kind of
Python,
done.
but is there an
Hi. Is there any specific support for monitoring multiple systems and looking at relationships between what different machines are doing and how they're causing performance on each other and that kind of thing?
Sorry, I didn't completely understand. You mean monitoring other systems than the current running one?
Yeah, or monitoring distributed systems running on multiple machines, yeah.
Yeah, we have a client server set up. So you could kind of spawn scripts on other machines, but it's not that much worked out yet.